All right, this is AP Statistics Chapter 10, and Chapter 10 is on re-expressing data to make it straight. All right, so what we spent the last couple of days we spent talking about when to use a linear model. And remember, there's two things that need to be checked in order to make sure a linear model is appropriate. First, the scatter plot itself, and that's the scatter plot of x versus y must be straight. Now, when we say straight, it's never going to be perfect, but we can't see a major curve. If you look at me like, wow, I see a curve, then obviously it's not straight. Also, the residual plot, and you remember the residuals is x versus the residuals, must show no pattern. Those are the two things that we check to make sure that we are, doing the right thing by using a linear straight model. Remember, the residuals, by the way, to find a residual, you do the actual y's minus the predicted y's, and our calculator makes that list for us, and then we just have to look at it against the x's to check the residual plot out. So one of the major issues that comes up in Chapter 10 is what happens when both of these things are violated, or maybe the scatter plot looks straight, but the residual plot has a clear curve to it. Or maybe the scatter plot is completely curved and the residual plot is completely curved as well, and both things would obviously be bad. What do? Well, we have to re-express the data. And there are several different ways to re-express the data. Now, just think about this for a second. Okay, I want to kind of talk to you about the two options. If your scatter plot has a complete obvious curve like that, one option is to, instead of using a straight line model, okay, instead of using a model that's a straight line, we could use a curved model. And there are things out there. There are curved models out there. But to be honest, in statistics, we try to stay away from the curved models. We like to use straight models. So the idea is when we have this curve, we want to still form a straight line to it, but we have to force the data. We have to make the data become straight. And to make the data become straight, we have to re-express it, okay? So our original data is x comma y. All of our original points are x comma y. And we have to exchange these values in order to make them straight. Now, there are several different options. I mean, I can go through a long list here, and I'm going to list several of them. But the most famous way, to be honest with you, the way that I see comes up most on the AP test, is to leave the x values alone, but take the log of the y values. So we're going to actually take the log of all the y values, changing all of them, and that sometimes makes the data straight. Another option is to take the square root of all the y values. Another option is to square all the y values. Another option would be to use a natural log. Now, I'm going to be completely honest with you. Using a natural log is going to probably yield something very, very similar to using a regular log. So some kids just like using logs, some like using natural logs. We'll talk about using both. Also, there's a case where you take the reciprocal of all the y's. You actually do 1 divided by all of the y's. There's a really weird case where you would do what we call 1 divided by the square root of y. So we actually take the square root of y and then inverse it. So those are all I'm going to tell you right now, the most common ways that we're going to see come up are using log and natural log. Not to say that any of these other ways aren't going to come up in an example 2 or 3. I'm just saying in terms of the AP test. Now, there's also some extreme cases where we don't just change y, we change x and y. So maybe we take the natural log of x and we take the natural log of y. So that really, really re-expresses the data. Or maybe we take the square root of x and leave the y alone. Another weirdly weird option is to take the reciprocal of both the x's and the y's. Now, there's a lot of options. Don't freak out and think, oh my God, how am I ever going to figure out what needs to be done to the data to make it straight? A lot of times it's just trial and error. I would always start by trying the natural log though. But after you re-express the data, the idea is to then look at the scatter plot of your re-expressed data. Is it straight? Look at the residual plot of your re-expressed data. Is it showing no pattern? Okay, so that's kind of what the goal is here. Now, let's take a look at an example. Okay, here's an example. It starts off like any other example. We have a table of values, and we're trying to figure out, since 1990, the tuition at Arizona State University has gone up. And we want to see if we can make some type of linear model that can predict how much the tuition at Arizona State University is going to be from the years since 1990. So we got X being the year since 99. We're trying to predict the tuition. So the first thing you could do is, if you want to do it right now with me, or if you just want to watch, it's up to you. You can pause the video, enter this data into your calculator. So let me show you how I did that. I already have it done here. Stat edit. List 1 would be the years 0 through 10. List 2 would be the tuitions. They're all there. You could trust me. So the first thing we would do is take a look at the scatter plot. Okay, so turn the scatter plot on. Make sure that it's list 1 versus list 2. That's where I have the X and Y list. And then we would do our classic zoom 9. Okay. And, oh boy, I don't know. Hold on, I got to see what happened. Here's, you know what? If something weird like that happens, I had 2 plots turned on at once, and the calculator is having issues with that. So zoom 9. Here we go. So take a look at that scatter plot. Remember, the first thing is to make sure the scatter plot looks straight enough, and I would definitely say that scatter plot looks straight enough. The next thing you want to do is check the residuals. Now, your residuals are not calculated until once you find the linear regression. So we're actually going to go ahead and run a linear regression. Make sure that you choose number 8 here, which is the linear regression A plus BX. And we're going to tell the calculator do list 1, comma, list 2. And it's going to actually run the linear regression for us. So it came up with this decent equation. Again, look at the r squared value, very high. Look at the r value, very high. There's my y-intercept, there's my slope. Now, the moment this is ran, the residuals are done for us, and they're stored in this list right here. If you want to look at second stat, you can see that list of residuals. I don't know, I've got a list called AA. I don't know what the heck that is. But anyway, down there at the very bottom is the residual list. So go back here to your plot. Now let's check out that residual plot. So you're going to go back, and remember, the residual plot is leaving the x's alone and changing the y list to the actual residuals. Excuse me. And I'm just going to go and grab that residual list there. And then don't forget, make sure to choose your favorite dot, whatever dot you want to choose. And then zoom 9. Now, if I look at this residual plot, I see a kind of a curved pattern where it's positive residuals, then some negatives, and then it curves back up. I mean, it's not a perfect curve. It's not the end of the world, but I do kind of notice a little bit of a pattern instead of seeing a nice mix. So this is an issue where I may need to re-express my data. So here's what we got to do. We got to go back to our original data here, and we have to start re-expressing it. But I don't want to delete any of the data I currently have. So let's see what I can do here. Now, let's go through our list. Remember, one of the first things we said is to try to log the y values. So notice, here's how I can do this all at once. I'm going to tell the calculator, take the log of all of the y values. That was list 2. So I'm actually going to log all of the y values. So doing this is going to log every value in list 2. And I'm going to store, the store button's right above on, I'm going to store that as list 3, which was just an empty list. So I'm going to currently, I don't want to replace list 2, so I still got list 2 as my y's. I'm going to store all these new values, they're all the logs, into list 3. Okay? So now that that's done for me, and by the way, if you want to go to your stat and check it out, there they all are in list 3. There's all those values right there. So now what I want to do is I want to check out my scatter plot. So I'm going to go back to my scatter plot, because remember, there's always 2 things you got to check: scatter plot, residual plot. So I'm going to go back, and I'm going to look at the X list versus list 3, which was the log of my values. And I'm going to take a look, and again, I always have to hit that zoom 9. You always got to make sure you hit zoom 9. And hey, okay, scatter plot looks really straight. Let's test the residuals. Okay, well, in order to test the residuals, I have to run a linear regression, because the residuals do not get ran until I run a linear regression. And I want to do linear regression A plus BX, but be careful, I got to do list 1, comma, list 3, because now I'm looking at I want to run a linear regression of list 1 versus the logs of the y's. And I get my values. Now look at this. R and R squared are both very high. Now if you remember what they were before, they were both high before, but they're actually even a little bit better, believe it or not. That's a good sign here. And then I got my slope, I got my y-intercept here. Let's take it, now that I did that, the residuals are ran. So let's go take a look at the residuals now. So it's a lot of clicking on your calculator to do all this, but it's worth it. So now I got to go change the y list to the residual list. And again, that residual list only gets updated after you run the linear regression, okay? zoom 9, and notice, oh, maybe you still see a pattern. I don't know. Maybe you do, maybe you don't. But if you notice, I did break the pattern up a little bit. It does look a little bit better. It doesn't look perfect, but maybe a little bit better than it did before. So the idea is that's what we're trying to do. We're trying to somehow break the pattern up so that it looks a little bit better. Okay? So maybe you don't agree that that is broken up, but it definitely is in the sense that I don't see such a clear pattern. And to be honest, guys, sometimes residual plot isn't going to ever look perfectly mixed up like you want. So let's go back to that linear regression here. And this is the pattern. This is the new equation that I want. Okay, so my y-intercept is 3.82, and my slope is 0.018. Okay, so now I'm going to come back and let's actually write out this equation. Okay, so we got the y-intercept was 3.82 plus the slope was 0.018 times the years. Now remember, that's the years since 1990. Now normally we would say this equals y hat, or my predicted tuition, but remember it's actually not, because we logged all of those, so it'd be log of that. So that's how it changes. Now that's the major difference. When we write out the equation, we log the y's, so the y right here, y hat, or the tuition predicted, needs to be logged. Alright, so this definitely made the data straight. The residual plot looked better. This is a linear line that goes through my data even though the y's got logged. So I re-expressed the data to make it straight. Okay, so now let's try to actually utilize this equation. So let's predict the tuition in 2011. So in 2011, that would be 11 years since 1990. So I have to do log of tuition, or y hat predicted, equals 3.82 plus 0.018 times 11. So I'm going to go to my calculator. I'm going to do that real easy. 3.82 plus 0.018 times 11. And I get 4.018. So I get log of y hat equals 4.018. Now hopefully you're like, wait a minute, there's no way the tuition in 2011 is going to be $4.02. Well, you're right, because this is log of y hat, or log of tuition. So I have to get rid of that log to actually solve for the predicted tuition. So I have an extra step in here. Now if you guys remember, the base of a log is 10. There's a little 10 right there. And to solve for this, I'm asking that you guys go back to pre-calculus and algebra a little bit, but this is actually really easy. It's 10 raised to the 4.08 equals y hat. So 10 raised to the 4.018 equals my predicted value, or my predicted tuition. And again, that's just the definition of a log. Remember, logs equal the exponents, and there's your base. So base 10, exponent is the 4.018. So now I'm going to go to my calculator. 10 raised to the 4.018 gives me a tuition of, my predicted value would be $10,000 and 423 and 17 cents. And that seems to fit the data. Looks like that would make sense in 2011. If the trend continues of the tuition going up, it does appear that the tuition is going to go up. So I re-expressed my data. I changed it. I changed it to try to make the data straight, the scatter plot straight, the residual plot showing at least a breaking up of the pattern. But then when I write out my equation, things are a little bit different. Now, what else changes? When you interpret r squared, remember r squared was 99% for this, you would say 99% of the variation in log of tuition is explained by the variation in years. When you explain the slope, you would say for every 1 year, the predicted log of tuition would go up by 0.018. So you got to be very careful that every time you're talking about the tuition, you're actually saying log of tuition now. All right, let's look at another example here, and let's do some trial and error with this one as well. All right, here we go. What happens is we notice that how many oranges are on a tree determines the size, the average size of fruit from that tree. So if you have a small tree that only has 50 oranges on it, the fruit on average are 0.6 of a pound. If you have 900 oranges on a tree, that's a lot of oranges on the tree, they actually weigh less. They're 0.38 on average of a pound. So it appears that, when there's more fruit on a tree, they don't grow as big probably because they're too crowded and don't have the room to grow big. So what I went ahead and did is I went ahead and plotted this on my calculator. And if you want to go ahead and hit pause and enter that in on your calculator, you can. So I want to show you what I did here is I knew that I was going to be having lots of data here, so I put that in list 3 and list 4. Oh, I take that back. List 4 and list 5. So list 4 would be my x's, list 5 would be my y's. I want to see if I could take the number of oranges on a tree and predict the size. Okay, so I got that in here. List 4 and list 5. So I'm going to take a look at the scatter plot first. So my original scatter plot is going to be the x's, list 4. So when you have other data in there, you just got to try to keep track of it. List 5. All right, so I'm going to pull the old zoom 9. And, if you look at that, a couple of days ago, you might have said, well, straight, very straight. But notice you actually kind of do see a slight curve in that data. But let's take a look at the residual plot. Again, the residual plot is not updated until I run a linear regression a plus bx. But got to be careful because this is list 4, comma, list 5. Okay? And notice r and r squared are not too bad. I got a negative value for slope here. That's because it's going down. Watch out here for slope. I got this e to negative 4. That means the slope is negative 0.0002558969. So be careful. Watch out for that. Don't, make sure you keep your eyes open for that kind of stuff. Now the residuals are ran. I can go ahead and take a look at the residual plot. And again, I'm going to leave the x list as list 4. Those were the number of oranges per tree. And I'm going to go ahead and change this to the residual list. And now that that's done, I can do the old zoom 9er. And whoa, yeah, pretty sure that's a curve. Okay, time to start to re-express my data. Got to figure out what to do. 99 out of 100 times you're going to leave x alone. So let's try to figure out what we could do to y. Well, we got done talking about natural log and logs. So let's take log of the y list here, which is list 5. Y, and I'm going to store that, and we could use list 6 is where I'm going to store. So I like to use 1, 2, and 3. Or 4, 5, and 6 when you're doing this. So anyway, list 5, remember, is my y's, and I'm going to store that as list 6. There they all are. So now let me take a look at the scatter plot here. So I'm going to do a scatter plot of list 4 versus list 6. List 6 are my new y's. And zoom 9, remember, always got to do zoom 9. Ooh, wow, really straight. Very nice and straight. But I got to check that residual plot. The residual plot cannot be checked until I run a linear regression. So I'm going to do linear regression of list 4, comma, list 6. Remember, list 6 is where I put those log values. And, okay, hey, r squared and r are pretty good. I don't know, it looks okay to me. Let's take a look at the residual plot now. Now that I did that, the residual should be updated. I'm going to go ahead and change that list 6, the y list, to the residual plot. And again, like I said, the hardest part about this is just you're constantly going around and around and around trying to solve these different things here. All right, let's see here. Okay, it should be good to go. Zoom 9. Okay, I did break it up. I mean, to be honest, I would probably accept that because it did break up quite a bit. I don't see an obvious curve, but I still do see a little bit of a curve. But like on the last problem, remember, sometimes you just try to do as best you can. I am going to continue on here because I think just from knowing the problem, I think there's a better one. But again, that's not bad. I would not have a problem with you actually using this data right here, which would be the natural log of the y's equals a plus bx in this case. But I think there's a better way, and it's just more because I know. But let's try another one here. Let's try something weird that we haven't done yet. Let's try the square root of list 5. That's my y list. And then we're going to store that as list 6. Make sure you close that parenthesis. So let's try the square roots. Maybe the square roots will work out here. So I re-expressed my data. I got to go back once again, and I got to check the scatter plot, which would be list 4 versus list 6. So once you're done with that, you pull the old zoom 9. Hey, it looks like it got straight, but I can't check the residuals until I run this linear regression. And I'm going to go list 4, comma, list 6 here. And hey, stuff looks good. R and R squared look good. I mean, if R and R squared get worse, obviously that's another sign that you're not on the right track. But everything looks good so far here. So now let me actually take a look at these residuals. And now that I ran the linear regression, the residuals should be ready for me to go. So you just got to constantly updating your graphs here and checking them out. So zoom 9. Still see a curve. Actually, the log one looked a lot better, but I still see a curve there. So, okay, life goes on. Let's try something else. Let's do 1 divided by list 5. Okay, and then let's store that as list 6. We're going to do 1 divided by. We're taking the reciprocal, 1 divided by it, and we're going to store that as list 6. Let's try this. So go back to my scatter plot. I'm going to change my Y list to list 6. And then I'm going to pull the old zoom 9. Whoa! Looks really straight. Wow, that looks really straight. Okay. Now I got to check the residuals. And I can't do that until I run a linear regression. So hopefully you're picking up on all the stuff you got to do here. List 4, comma list 6. And again, remember list 6 was 1 divided by my Y values. And whoa, R and R squared got really, really good. Things are looking nice, but they were looking nice the other ways too. But let's just check this out here. And again, now that my residuals are done, you always have to remember to do that first for your residuals to be done. Okay, zoom 9, and wow, that looks good. Look at that. That is a nice mix of residuals. I got positives all the way across the top, negatives all the way across the bottom. Wow, that looks pretty good. So it looks like this is the way I want to go. So I got y-intercept of 1.60, slope of 0.0011. So now let's actually write this out. So my y-hat is, remember we took 1 divided by my predicted y's. So 1 divided by my predicted average fruit size equals 1.60 plus 0.0011 times the oranges, how many oranges you have per tree. All right. So now let's use this to actually make a prediction. So let's say that I have a tree that has 375 oranges total on it. How big could I expect those to be? Well, 1 divided by my y-hat, let's see here, 1.6 plus 0.0011 times, 375 is going to give me 2.0125. Now, obviously, that doesn't mean my oranges are going to weigh 2.01 pounds. That doesn't even fit the data, but I got to do the actual inverse here. So remember, the idea is how do I solve for the y-hat on the bottom? Well, one thing you can do is cross multiply, and you get 2.0125 y-hat equals 1. And then you actually have to divide by the 2.0125. So 1 divided by 2.0125 gives me 0.497. So 0.497. And that fits right in with the data. Look at that. 0.497 fits right in with the data. And that would be 0.497 pounds. So hopefully you've learned a little bit from watching this video. It's all about trying to re-express the data to make it straight here. Okay, and you got to play a lot on your calculator to try to work it out. Hopefully I've kind of taught you the process you need to go through, but the whole time you're always checking your scatter plot to make sure it's straight, and you're always checking your residual plot to make sure they show no pattern. Again, all different kind of ways to re-express the data. I will say that using the log and natural log are number 1 probably on the list, but we saw this one right here where I used a 1 divided by the square root of y to come up with the values. Again, this one right here is very rare. These ones over here are all very rare. The ones I see most often coming up on the AP tests are logging, square rooting, or reciprocating. So hopefully you'll be able to work on a couple problems where this comes up. Like I said, the number 1 goal I want you to simply, be able to do is just play around with the equation. Once you have the equation, you have to understand that what changes in the equation, it's no longer y predicted, it's log of y predicted because you took the y's of all of them. Or it's no longer y predicted, it's 1 divided by the y predicted, okay? So it's usually just kind of being able with that, or being able to play around with that. When you see a computer output, it'll actually say, instead of saying, the dependent variable is average fruit size, it'll actually say it's the reciprocal of the average fruit size. It'll say 1 divided by the fruit size. Or up here, it'll actually say log of the tuition, so that you know that it did that. It is possible to log or reciprocate or do something with the x's. It's just kind of rare, but it does happen. So hopefully we'll see enough examples next couple days. Honestly, guys, being able to do all that work on the calculator that I just did isn't my number one objective for you. You need to kind of be aware of how to do it. My number one objective is that you could understand that when you re-express the data, why did you do it? Scatterplot, straight, residual plot, no pattern. And how do you then play with the data once the data has been re-expressed? How do you actually plug values in and solve for them? Like right here, we had to do this, raise everything to the 10. We do 10 raised to the 4.018 to solve for it. This other one right down here, once we plugged our value in for oranges, we had to cross multiply and solve for y hat. And that's oftentimes the toughest part. But like I said, 99% is the r squared. So that means 99% of the reciprocal of the average fruit size, or the variation in the reciprocal of the average fruit size, is explained by the variation in the number of oranges. So how you give those r squared values change. Also how you give the slope. This slope right here of 0.001 would tell me for every one orange that I increase per tree, the predicted reciprocal of the average fruit size increases by 0.0011. So you have to make sure that when you're giving all those kind of statements, those kind of things are included in there. Okay? All right, so hopefully this video made sense. We're going to do practice with this on Monday and Tuesday. Thursday, and then again on Tuesday when I see you guys. And then I also have the review packet for you for the big test for you to start practicing with. All of this stuff right here is important to know, but it is a small part of the actual big test because the big test covers a lot actually. All right, so have fun. I'll talk to you guys later.